Hello dear friends, a great welcome to Idea Statica tutorial. Myself Jaraj and P. It's probably 2 months since I have uploaded any tutorial videos related to Idea Statica. With this tutorial, we are going to launch a new series on seismic assessment of various connections using Idea Statica. This is tutorial number 29 and covers the seismic assessment of an unstiffened extended end plate bolted connection following the guidelines prescribed in EC3, in particular for stay structures and for connections, and also using the guidelines prescribed in EC8. So let us start Idea Statica tutorial number 29. Please note that the link for the playlist for all earlier tutorials is given under the description of this video. So the beam column connection considered in this tutorial is shown here. It essentially is a joint corresponding to an external column beam connection, or we can call it as an exterior joint. And as shown in the figure, this is an unstiffened extended end plate bolted connection for an exterior joint. So basically the seismic assessment procedure consists of the various steps. Before stepping into Idea Statica for the seismic assessment, we need to complete some homework, which is described here essentially. And the first such procedure is the design of the joint. So we have carried out a structural analysis of the given structure, and corresponding to the given joint, we can obtain all the design forces, corresponding to the critical load combinations involving the earthquake loads. Now, using these earthquake loads, we need to design the joint. And once the joint is designed, we need to move to the step 2. That is basically classifying the designed joint based on its strength as well as the stiffness. Now, based on its strength, we need to classify the designed joint either as a full strength, equal strength, or a partial strength connection. And then we proceed to step 3. That is, we are going to classify the design connection based on its stiffness. So based on the requirements given in the Eurocode, it is possible for us to classify the connection either as rigid, bent, or semi-rigid. And once the classification of the joint is over, we need to perform the necessary checks for the required joint resistance and pre-selected dissipative components. So let me take a very simple example that covers all these 4 procedures, including the demonstration of Idea Statica for the seismic assessment. So the structural analysis provides us the critical load combinations, and based on this process, I have designed a typical exterior beam column joint that essentially uses an extended end plate that uses with the bolts. And the connection that is designed follows the norms prescribed in IN 1993-18-2005. As you can see that this is essentially a column beam connection, and the column is HE360A and the beam is of IP400. The end plate that is used is 25 mm thick, and as you can see that a total of 8 numbers of bolts are used, and the bolts used are of M30 of grade 10.9, and the end plate is of dimensions 250 by 600 mm. So now we proceed to step 2, that is, we need to classify the designed joint based on its strength. Now the strength assessment of a given joint can be conveniently done using the component method. I would suggest my friends, please perform the necessary required calculations using the component method. And the basic advantage of this component method is it derives the joint resistance based on the resistance of the various components highlighted in Eurocode, and it also provides us a sufficient insight which of the components are very decisive. That means which components will govern the moment of resistance of the design joints. For example, for the design joint, I have performed a component method, and as you can see that the component method involves performing almost a similar type of calculations for various type of components. And this can be easily programmed in various programming platforms, like for example you go to the MATLAB or the Visual Basic, and it can also be done using any calculations that will make the computations, repetitive computations can be performed with a lot of saving in the time. So in this case, I have performed a component method calculation which provide me the resistance of the row 1 of the bolts. Row 1 means is the first row which stands above the tension flange of the beam. It has got a resistance of 595 kilonewton, and here I have seen that the decisive component that governs the resistance of row 1 bolts, it is the column flange in bending. Similarly, considering the failure of the T-stub mechanism, I have also obtained the resistance of row 2 of bolts, and that works out to be 382 kilonewton. And obviously here the decisive component is different, that's a column wall in shear. Or in other words, you can say that the resistance of row 1 and row 2 is essentially governed by the column web panel. So now considering the resistances F1 and F2 corresponding to rows 1 and 2 and the location from the center of compression, we can readily calculate the moment of resistance of the connection MGRD as F1 Z1 plus F2 Z2, and this works out to be 389 kilonewton meter. Having obtained the moment of resistance of the connection, let us go ahead for the classification of the joint based on the strength. Now, if we would have designed this connection as an equal strength connection, it should have a strength that corresponds to the full plastic strength of the connected beam IP400, which works out to be 464 kilonewton meter. On the other hand, if this connection is to be qualified as a full strength connection, which is recommended in the Euro codes, it should have a higher moment of strength, that is equal to 638 kilonewton meter, which obviously take care of the possible increase in the yield strength and also the strain hardening factors in the computation. Obviously, we find here that the moment of resistance of the connection is only 389 kilonewton meter, which implies that it neither belongs to an equal strength connection or a full strength connection. And accordingly, we can classify the designed connection as a partial strength connection. So we complete step 2. Now let us move to step 3 of the assessment procedure. In step 3, we obtain or we compute the stiffness of the designed joint, and as usual, the stiffness of the assigned joint is to be obtained from the stiffness of its component following clause 5.2.2 and 6.3.2 of EN 1193-18-2005. So the moment rotation curve that is developed for the joint is given here. As computed from this plot, the initial stiffness of the connection works out to be 151.9 meganewton meter per radians. Now, as prescribed by EN 1993-18-2005, the limiting value for a rigid connection works out to be 202.14 meganewton meter per rad. Obviously, the initial stiffness happens to be less than the limiting value, and accordingly, we can classify this connection as a semi-rigid one, and the rotation capacity associated with this connection works out to be 46.5 milliradians. So please note that we have developed a connection that is semi-rigid and of partial strength. Now the question arises, does Eurocode support this kind of connections? Yes, obviously, EN 19981-2004 permits the use of dissipative semi-rigid or partial strength connections, but obviously it provides us a number of conditions to be satisfied if these type of connections are to be used in any type of structures for the dissipation of the seismic energy. So now let us move to step number 4. Now is the right time that we go ahead with the Idea Statica, which uses the capacity design for the verification of its various components. Now for this particular calculation, the connected beam IP400 is chosen as the dissipative component for verification, and the calculation shows that as per the capacity design, the connection is able to provide a resistance of 355 kilonewton meter, which works out to be 76.5% of the moment of resistance or the plastic moment of resistance of the connected beam IP400. And under this applied moment, the maximum plastic strain in the other parts is worked out to be 4%, which is less than 5%, and the utilization of the boards is 88.9, which is less than 100%. Therefore, the design connection passes all the checks. So now let me demonstrate you how to use Idea Statica for the seismic assessment. So the model used for the seismic assessment is shown here. And before you go for the capacity design, ensure that in that ribbon on the leftmost side, you select the CT, which indicates the capacity design. Okay, so let me quickly take you to a brief description of the model. So let me just go to the design. So as you can see that the column is an HA 360 member, and the model type is chosen to be an NVM model, and coming to the beam is an IP400 beam. And here please ensure that we have chosen the NVZMY model for the application of the loads, and the forces are being applied at a pre-calculated position which happens to match with the face of the end plate. So that's regarding the beam specification, and we need to check the capacity of this design connection using some load combinations. And here, for example, I have set the moment to be tested, or the joint moment of resistance of 355, and under this moment of 355 kilonewton meter, we need to check whether all components pass the test or not. Now let me take you to the other manufacturing operation, the end plate. As you can see that the end plate is connected to the beam of IP400, and it is of grade S355, which matches with the grades of all beams and columns, and has got a thickness of 25 mm, and the connection type is bolted, and the locations are all prescribed here. And the bolts, as already detailed and discussed, it's a FAM30 grade 10.9, and the row locations are specifically provided here. And one very important thing I would like to tell you is that all the flange as well as the web elements are being connected using the full penetration butt weld, which is also the groove weld. Okay, and the specification of, as you can see that, to improve what we call as the capacity of the column flange and also the column web shear panel, we have introduced the continuity plates which are being modeled using the manufacturing operation stiff. And as you can see that the continuity plates are of 15 mm thick, and they are also connected to both the flange as well as the web of the column using the butt welds. And that is all regarding the manufacturing operations. For the description of the various components in the modeling procedure, and here finally I have selected a dissipative component, and this required dissipative components can be added by pressing this item, that is a dissipative item. And normally when we go for the full strength analysis, by the dissipative item we mean the weakest link in the entire system, right? And this weakest link is given some kind of an overstrength, considering the increase in the yield strength from the consideration of the what we call as the nominal yield strength, and also from the consideration of the strain hardening. And here I have chosen, as you can see, that IP400 as the dissipative component. And how to select a dissipative component is very simple. What you do is that you need to press this. You may suppose, for example, we want to add a dissipative additional component in addition to IP400. For example, let us say that I want to add the end plate also. So the procedure is very simple. What we need to do is that we just press this label, that is a dissipative item, press it. So you'll find that a new dissipative component appears over here. And here, as you can see, that nothing selected. So here, suppose you are interested in making the end plate as a dissipative as one of your design objective. So what you need to do is that you press this button. So here it is written pick by mouse cursor. So you pick this. So what you need to do is that you highlight this end plate, and after highlighting, please enter the button. Okay, please press the enter button. So here you will find that the end plate EP1 is selected, and here is a provision that is given in specifying the properties of this dissipative component, which is very important. That's a strain hardening. So as per the Eurocode, we provide, you go for a strain hardening. Normally, if you are talking about the EC3 connections or the EC3 main, so you'll find that a strain hardening factor of 1.1 is prescribed, but in the modified EC, you'll find a strain hardening factor of 1.2. So this is what is being used over here. So what we can do, so this is how you go on adding the different kinds of what we call as the dissipative components over here. So let me just delete this. So if you want to delete this 4, what you just select it and delete it. Okay. So so you will find that the capacity design procedure is almost like any other procedure, except that the main difference being you have to press the CD button, and also one important manufacturing operation, that is the dissipative item, has to be added in this procedure. So just like the other procedure, just press the calculate button in order to find out the results, whether the various components pass the checks or not. And based on that, we need to upgrade the moment that is input into the model for the verification. So let us wait for the Idea Statica to complete the calculation, and we will find out what will be the actual calculated values for the components, such as, for example, the plates, bolts, etc. And based on which we will take the decision whether the analyzed design model is correct for the inputted moment or not. Yes, the analysis is complete. We find that the plates is subject to a strain level of 4%, which appears to be less than the prescribed limit of 5%. And we find that the bolts have got a utilization of 88.9%, which is less than 100%. So now, this is one very important thing. So that is, though in this particular case, we are doing a partial strength connection, we don't expect any kind of a plastic hinge mechanism in either the connected beam nor anywhere else in the structure, but we will find that some of the components are getting severely strained. So in order to get what we call as the strain distribution, let us go for the check, and the check will be able to find out the strain distribution and which are the critical elements. So just press the plastic strain, and you'll find here that okay, let us just mesh it. Okay, yes, it is already meshed. So here you'll find that one very important thing, just a minute, let me just keep the deformation later, and I will apply the mesh here. Yes, so as you can see that in this case, the first one component, let us go by step. So here is the column web, and here you find that in the column web, the beam web, we don't have much problem. Let me take the top flange. Yes, in the top flange, we find that a part of the flange, it is strained, and coming to the bottom flange, yes, the bottom flange also we have a strain levels of the order of approximately, you can say that 1.75 to 2%. And now the important decisive components, as we have discussed in the seismic assessment, happens to be what we call as the web panel. So let me just zoom this. Yes, this is our web panel. So, and as you can see that we have a larger amount of a strain getting developed in the web panel zone. So now let me just press this panel and obtain this. Yes, so you will find that here we have got a larger concentration of the strains, and these strains, let us just go into this, simply inspect this table and see which of the components are critical as far as we are concerned. So you find that yes, HEA360 web, that it happens to be the what we call as the shear panel, it has got a strain level of 3.3%. So this is a critical component as far as we are concerned. And then we have yes, one more component over here, that is with a 4, and we find that here the end plate, yes, the end plate has also got a strain level of 4%. So it happens, though we have selected our beam as the dissipative component, the maximum strains we are finding out in other components, because we find that actually the capacity of the connection is in turn dictated by the column web shear panel as well as the end plate. So here we find that the strain levels in the end panel and plate has also gone to the tune of 4%. Okay, so these are the two critical panels or the components that affect what we call as the seismic load bearing capacity of this connection. So please remember that here we have checked the connection for a moment of 355 kilonewton meter. So as usual, let us see, for example, what would be the deformed shape of this joint, and this deformed shape will eventually help us whether there is any kind of a plastic hinging occurring anywhere along the zone. Here we find that a single view of this deformed shape tells us that there is no kind of a plastic hinging process. Obviously, there cannot be any plastic hinging process here because we have designed it as a what we call as a partial strength connection, and we have seen that the strain levels are well within 4% as well as the connected beam is concerned. So we find that so there are no kind of a hinging as the deformed shape of the joint tells us. Now, in order to obtain the final the report, let us just press the report button. So here, please also see how the factors like, for example, the overstrength, the strain hardening is getting reflected in the final calculations. That is also interesting to us. So we will see what are the elements that is chosen as a distributive component and what exactly are their actual strengths used. So here, if you go down, you will find one very interesting thing, that is yes. So first of all, this is the result summary. You find that the result summary shows everything has passed the checks, and finally, if you go into the table containing the plates, you find that the three component, there's a one component, that's the IPE 400. It's considered as a dissipative component, and accordingly you'll find that the material is marked with a star, S355 star. And here S355 star means you can see that this component during the assessment is assigned a higher yield strength using an overstrength factor of 1.25 and a strain hardening factor of 1.2, right? And we have limited the deformation or the strain level of this component to 5%. So that is very important to note down. So please remember that as far as the dissipative component is concerned, Idea Statica will assign a higher strength level or a higher stress level, which is based on what we call as the overstrength factor as well as the strain hardening factor. And based on this higher overstrength in the dissipative component, the various balanced components which are what we call as identified as non-dissipative will be verified by Idea Statica, and then based on these results we can find out whether the computed capacity is okay for us or not. And looking into this table, we also find one very important thing, that is the connection is checked for a capacity level of 355 kilonewton meter, for which we find that the results are okay for all the components. So my dear friends, so that's all about the demonstration. As you will find that the seismic assessment, it hardly takes what we call as 5 to 10 minutes of time. But what is very important is that the seismic assessment cannot be straight away done using the Idea Statica, because the engineer need to know actually the sequence of what we call as the dissipation or the strength hierarchy of the various components of the joint if he wants to get an insight into the overall performance of the joint. So in my opinion, I have spent almost as much as 1 week time for the homework calculations. For example, in obtaining the strength capacity using the component methods, in obtaining the stiffness, and having done this calculation, application of the Idea Statica is a very simple procedures, and it is up to the engineer to see whether how to interpret the results given by Idea Statica. And let me just tell you, in this very specific case, we have designed a partial strength joints, and in the EC, the European code in its present form do not have much detailed implementation of the partial strength joints, but as specified by the code, The use of such partial strength or what we call as a semi-rigid connections has to be established by actually performing the inelastic or the nonlinear analysis of the structure. And normally what I do is that whenever I have this kind of a structure which involves a semi-rigid partial strength, I normally go ahead with two ways of structural analysis. I perform either what we call as a static pushover analysis, and that will let me know whether the joints will be capable of taking the structure to the desired deformation levels with a capacity well in place, that is without any capacity degradation. Or otherwise what I will do is that I'll go for some a higher advanced version, like for example an incremental dynamic analysis that will also let me track whether the joints that is being properly modeled as the nonlinear elements, whether they are capable of undergoing the significant rotation capacity without any degradation of the what we call as the joint strength. So these are very important procedures when we need to go for what we call as the what we call partial strength or a semi-rigid connection, because there are specialized versions. In fact, for big structures or very critical industrial structures, we need to qualify the designed joint either using the test a series of tests that is done in the lab, or we need to use a software that has successfully verified numerically the established databases available in the various valuable projects, and then use this same for our specific joint, and through the numerical analysis and a proper loading procedure we'll be able to check the what we call as the acceptability of the design joint. So that's all about this tutorial. I will take you to a different kind of a joint in the coming tutorial. Thanks a lot for listening.